So we are doing waves today. Sorry. So waves can come in many forms. They can come in light, sound, energy, UV, X-ray, and this big word here, electro, and it so happens to be in the electromagnetic spectrum, which also adds microwaves. It has radio waves. There is visible light. There is gamma rays, and a whole heap more. So I I won't cover too much of this topic, but I'll just go over the basics. So this A represents our amplitude, which our amplitude is the measure from our crest to our starting point, which if we see at this point, let's call this 0, 0. Because in theory, this is just your y-axis, and this is your x-axis. So that is your amplitude. It's a measure from the crest to your starting point. Now your cycle is this orange line. It's not the actual orange line, but your cycle is this. So what a cycle is it's one wave in a period. So this is your period. A period is the whole duration of the wave. So one cycle could be in that wave. So you can have, so here we can count. So we've got one cycle here, we've got two cycles, and we've got half a cycle. So we have 2.5 cycles. And our frequency is the measure of one cycle in a minute. Oh, sorry, not in a minute, in a second. So that's why you get the equation frequency equals 1 over period. This is your wavelength. It's measured in meters, and it measures crest to crest. So how far each wave, how far each wave is from each other. So let's say your amplitude is 5 meters, and your crest is at 5 meters, and your trough, which is the bottom part of the wave, is at -4 meters. So to find the midpoint, which is generally your middle point here, so let's say we've got 10 and we've got 2. To find the midpoint, you take the average of the crest and the trough. Sorry. So we have 10. That is our maximum plus -2 divided by 2, because we have two numbers, 1 and 2. We can only have 2, really. So if we do the maths, 10 minus 2, that is 8 divided by 2. So our midpoint is at 4 meters. Let's call this meters. Let's call this meters. So our midpoint, will be about here. So that's where our midpoint would be. And that's when you can start finding the wavelength, the period, the cycles, and the frequency. So let's get into the types of waves. Or we could probably get into wave speeds. So when you're dealing with wave speeds, if it's, let's say it is V equals frequency times lambda. Oh, by the way, the symbol for frequency, the symbol for wavelength is called lambda. So velocity equals frequency times the wavelength. So let's say our frequency, let's say we're trying to find our frequency. So frequency equals velocity over lambda. Let's say lambda equals, say lambda equals 2 meters. And our velocity equals 10 meters per second. So that means our frequency will equal 10 meters per second divided by 2 meters. Now I'm going to get my red pen out and I'll show you a trick. So if we look at this 10, look at this 2, we obviously know it's going to equal 5. But let's look at these two m's. So we got m and we got m. If we look at this m, I'm actually going to rewrite that and give us a easier interpretation. So let's put, oh, I don't know what that was. Let's put an m over the s. So we've cancelled the m, and we actually have to cancel both m's. So now we are left with 5 seconds. But remember, the second is in the denominator. If it was in the numerator, then it would just say, it would remain as 5 seconds. But since it's in the denominator, we have to call it seconds minus 1. And this is what you call a hertz, or 5 hertz. So just remember, when you're transpositioning to find, velocity or to find frequency, then the lambda is measured in meters, which cancels out with the meters inside of the velocity, which is measured as meters per second. So that can help sometimes. So let's get into the two waves that we have. So we have something called a transverse wave. And a transverse wave looks sort of like the typical wave that you'd expect. And so it would be moving in a x direction, so it'd be moving on its x-axis, while it oscillates. Oscillating means that it's just in disturbance. So, and waves normally oscillate. So just think of like when you are vacuuming and or like any power cord you have, and you quickly flick up the cord, it'll make this motion until it reaches the plug. So think of a power cord. It's not really a good power cord, but and you got a little toaster. So just imagine you grab that power cord and you flick it up. So you flick it up and it says it oscillates perpendicular. So perpendicular is when there is a line moving horizontally, but at the same time there's a line moving vertically. So that's why you get this symbol. This is the symbol for perpendicular. Now longitudinal waves oscillate parallel to its motion. So it'll be moving in the x-axis while it oscillates in the x-axis. So think of like a slinky. Think of like a slinky here, and it pushes. So every time you pull it out and then bring it back in, it'll sort of vibrate, but it won't go up and down unless you use a force to move it vertically. So to force it vertically. But when you're passing it along your hands, it'll push that energy through the slinky, and it will eventually reach the other side. So it's hard without a slinky actually doing it. But if you search up slinky demonstration of longitudinal waves, then it'll show you exactly where the energy travels through the slinky. So when this, I recommend studying this part. So there may be a couple questions where it'll ask you to identify the sort of where the wavelengths and the frequency of longitudinal waves. So compression is when you've got a lot of energy in one area. So that's the wave moving. Refraction is when it extends. So when there is a sort of gap, or maybe the energy is coming to that point where it compresses. But refraction, it's hard to, rarefaction is when there's not a lot of energy passing through the point. So just imagine, so it's pretty easy to identify which one is which. So just remember that transverse is perpendicular and longitudinal is parallel. So this is another wave property. So this is called destructive interference. This is when a wave, so let's call this 5 meters, and let's call this trough -3 meters. So if a second wave has a trough of -3 meters and a peak of 5 meters, then but they oscillate in different periods. See this period here, it oscillates. It oscillates opposite to the first wave, which oscillates in a sort of, yeah. So this will cancel out. Both waves will cancel out. Whereas constructive interference is when you have a wave and a second wave sort of adding onto the first wave, so it has an increase. So that means it doubles the amplitude. So that's why when you, let's say you have a tuning fork, which is a little thing like that. Let's say this was 32 hertz, and you had a second one here. So the waves will travel through these. If these are the same frequency, these will travel through, and let's say you have a ball here, so the waves will travel through, creating motion where the ball starts to move every time it touches the second tuning fork. So I recommend watching videos on, this is what I'll recommend. So start watching for your exams. Watch the what's his name? The organic chemistry tutor. He's really great, especially for topics like waves, where I'm not, it's been a long time since I've done waves, and this is probably the best I can do. But if you want to start studying for your exam in waves, then this is probably the best guy to help you with your problems. Yeah, so that is a introduction to waves. Hope you liked it, and goodbye.